shell arced into the night and did something a shell was never supposed to do. It waited, not for a clockwork timer to run down, not for metal to strike metal. It waited for distance. In the Second World War, anti-aircraft fire was always a math problem with a cruel punchline. Even a well-aimed burst could be a clean miss if the shell detonated too early or too late. A contact fuse demanded the impossible, an actual hit on a fast, weaving airplane. A mechanical time fuse demanded perfection, an explosion within a narrow window of space and time, with wind, speed, altitude, and human stress all conspiring to ruin the calculation. In practice, the sky was defended by probability. Throw enough fragments into enough air, long enough, and eventually something breaks. The sky looked busy. The ledger looked bleak. The proximity fuse, known as VT for variable time, changed that logic by moving the explosion to the only place that mattered. The optimal zone, close enough for lethal fragments to intersect an airplane's vulnerable skin, but far enough to avoid needing a direct hit. That single shift is why VT is so often described like a miracle. But the colder truth is more important. The fuse did not win on its own. It worked because an entire system worked. Radar that could see, directors that could compute, crews trained to trust. Instruments, factories able to produce enormous quantities of consistent parts, and a doctrine that turned all of it into repeatable kill rate. The shell wasn't smart. The system was. The secret of VT starts with what anti-aircraft gunnery truly was. It was not shooting. It was prediction. A gun did not fire at an airplane. It fired at a future point in space, hoping a cloud of fragments would occupy the same volume as the aircraft at the same instant. Without VT, that future point also required a detonation time set by hand, set under pressure, set with small errors that became large misses. A fraction of a second could be the difference between a kill and harmless fireworks. That is why pre-VT engagements could burn huge amounts of ammunition for modest results. VT attacked the timing problem at its root. Inside the fuse was a tiny radio set. As the shell approached an aircraft, reflected signals changed in a predictable way, and the fuse fired the detonator automatically. The shell did not need to hit. It only needed to pass near. That sounds simple because it is easy to say in one sentence. Building it was another world. Entirely. Miniature electronics had to survive the violence of firing, forces that would shred ordinary devices, and then function reliably in cold air, vibration, and rotation. The achievement was not just scientific. It was industrial and procedural, making something delicate rugged, making something complex dependable, making something secret mass-producible. But even a shell that can decide when to explode still needs to be sent into the right neighborhood of airspace. That is where sensors and computation become the quiet killers. The fuse's optimal burst zone meant little if the burst happened in the wrong patch of sky. Kill rate gains came from shrinking two errors at once, aiming error and timing error. VT reduced timing error by detonating near the target. Radar tracking and fire control computation reduced aiming error by seeing the target precisely and updating the solution continuously. When both errors shrink, probability changes shape. This is why wartime leaders talked about effectiveness, not romance. Effectiveness is the whole chain: detection, tracking, calculation, fuse function, crew drill, ammunition supply, and sustained rate of fire. VT was a component that unlocked the value of the chain. Without radar eyes, a director's math, trained hands, and steady logistics, VT would be only a better fuse. With the system, it became a multiplier. The war exposed a hard reality. The enemy does not present perfect targets. Weather, smoke, altitude changes, evasive turns, poor visibility, and sheer exhaustion all destroy precision. A time fuse punishes small mistakes. VT forgives them, because close enough becomes lethal. That forgiveness is not softness. It is brutality by design. It turns near misses into kills. It turns imperfect prediction into acceptable probability. It turns stress into something survivable, at least for the defenders. Nowhere was that arithmetic more emotionally visible than at sea, when attackers began using suicide dives. A diving aircraft is not just a target. It is a countdown. The ship has seconds to stop it. Every layer matters. But heavy dual-purpose guns became dramatically more lethal when firing VT-fused shells. The reason again is geometry and timing. A shell that bursts at the optimal distance can shred control surfaces, rupture fuel, wound the pilot, or knock the aircraft off its dive path. Not every success shows up as a clean kill on paper. Many show up as something quieter, a ship that still floats at the end of the day. And this is where the data-first view matters. VT did not need to be used in every round to change outcomes. Even partial adoption could deliver disproportionate results because the kill mechanism was fundamentally different. If a portion of the barrage consistently bursts in the optimal zone, the defender's effective lethality per round jumps, even while the rest of the rounds remain conventional. That is the signature of a multiplier. It bends the curve without needing to replace the entire arsenal overnight. But the story gets even more revealing when it leaves the gun mount and enters the factory. A proximity fuse was not a boutique instrument. It had to be manufactured in enormous quantities with consistent reliability. That meant suppliers, standardized parts, test rigs, inspection routines, and quality control strong enough to prevent subtle failures at scale. It meant a workforce and an industrial ecosystem that could take fragile electronics and make them behave like artillery components. It meant that the battlefield was being shaped long before the first shell left the barrel. This is why the technology wins wars myth misses the point. The Second World War was won by systems that could absorb shock and keep functioning, systems that could learn, standardize, and scale. VT is the perfect example because it invites the wrong conclusion. It looks like a magic bullet, a device that turns ordinary gunnery into guaranteed kills. In reality, it is an amplifier. It made good detection more lethal. It made good computation more forgiving. It made training pay off faster because near-correct solutions became decisive. It made industrial discipline visible in the sky. And the system included secrecy and doctrine, not just hardware. VT was treated as a strategic advantage. Early use had to consider the risk of unexploded fuses being recovered and studied. Deployment choices were shaped by that fear. That is another systems lesson. Even the best weapon is only as useful as the strategy that protects its advantage long enough to matter. Then VT moved beyond the sea. The physics stayed the same. Only the target changed. An artillery shell that airbursts above troops does not bury its fragments in dirt. It throws them outward and downward. It turns cover into a lie if the burst happens at the right height and distance. On the ground, VT could be terrifying because it punished the one survival instinct infantry relied on, getting low and trusting Earth to absorb the blast. Again, the key is not smarter shell. It is optimal burst zone, enforced automatically at scale. That word, scale, should linger. One clever fuse is a curiosity. Millions of reliable fuses, integrated with radar, computation, training, doctrine, and logistics, is a war-winning instrument. Industrial war rewards repeatable processes more than heroic moments. Function beats elegance. Speed beats perfection. The enemy does not wait for perfect repairs, perfect procedures, or perfect calculations. The enemy only cares whether the defense works tonight. So the VT story is not just about a device. It is a story about a civilization's ability to turn information into force with minimal delay. Radar finds the threat. The director predicts its future. The guns throw steel into that future. VT forces the explosion into the optimal zone. Training keeps the rhythm. Logistics keeps the guns fed. Production keeps the parts consistent. When all of that is aligned, the sky stops being a place of chance and becomes a place of accounting. A shell in flight could not think, but it could be given one rule: explode when close. And when that rule was fused to radar, eyes, mechanical minds, drilled hands, and an economy that could replace everything that broke, the air itself became harder to cross. That is why VD raised kill rate. Not because it was magic, because it was the final link in a chain designed to turn measurement into lethality. At the end of this story, the uncomfortable question remains: which was more dangerous, the new device, or the system that could build it by the million, train men to trust it, and measure its results without blinking?